All right, class. Ready to get started? All right. So today we're going to be starting a new chapter, chapter 5 on dimensional analysis. I know you have an exam coming up today. So today we will be talking about math. Math will be considerably easier than the math we were doing in last chapter. Yeah, I think you'll see that. I hope you'll see it. It is Friday. We're going to look at YouTube videos illustrating some things we've seen previously, and also setting the stage for what we're about to do in dimensional analysis. But before we begin, any questions? Yeah. Next week on Wednesday, the test. Try to make it a letter homework this week. There's only 3 problems. There is a derivation on one of the problems, but it does follow along the rest of the framework. So it is a lighter homework this week because I got to do it this week. But I do want to make sure you get it. But yeah, so I have tried to do this. Sorry, that was awesome. All right. Any other questions? Okay. All right. So we start with this. This is another video illustrating the no subdivision, which I think is kind of a nice demonstration. Again, we looked at the dye in a microchannel, right? A short little video of dye flowing through a microchannel and getting stuck in the walls. This is in a considerably larger channel, right? So something that's maybe off the stage or so. And we'll see no subdivision in action again. Just as a reminder that seems like it shouldn't be true, but it is. So the setup here, this is the bottom wall that we're looking at. I know it's a little blurry. This is the bottom wall of like some big open channel or some big channel with transparent sidewalls. And what the experimenter is going to do here is put introduce dye through this tube. And then we're going to see what happens to the dye when they introduce it all the way to this bottom wall versus up in the middle of the So here they're putting it at the bottom wall. We can see it basically remains. There is some dye moving away. That's up in the free stream, but we can see that when they release dye up in the middle, it's basically just immediately goes away. Right, that dye at the bottom remains until they mix all that fluid away from the wall, and then it gets swept away. Okay. So another illustration of this slip. And this is going to come up in the next video as well. That can also include a demonstration of it. I'm sorry, the video is after this. So we're going to talk about today. We're going to talk about dimensional analysis. We're going to introduce everyone to dimensional analysis. And one of the things that we can do with this technique is just by looking at the dimensions of variables that govern a problem. So without knowing the details of exactly what the solution to that problem is, you still learn some really important fundamental things. And so one example that we'll look at is falling ball through a viscous fluid. You'll see an illustration of that in the video. We have falling ball and viscous fluid. Later in this class, in chapter 7, we're going to talk about flow around objects, or external flows. Talk a little bit more about what the drag force, covering the drag force on something like this. But even before we know the details of how you drag this thing or what the flow looks like, just by looking at the variables involved and their dimensions, we can make some really important conclusions about what goes on in this kind of problem. So we're going to look at this ball falling through water and this ball falling through glycerin or viscous fluid. We'll see differences, and we'll be able to say something about those differences, or at least the form of those differences, just by looking at dimensions. Right, so this is the ball falling through water. Now this is essentially a volleyball speedometer thing. We're doing volleyball speedometer in lab. We have a can, that. It used to be a lab. I don't know. So this is a way of measuring essentially viscosity of fluid. Is by we take some kind of a ball bearing or something, drop it through a fluid, and what's shown here are tick marks. You would basically, a really inexpensive way to do this is take stopwatch and measure time it takes the ball to line together. And then using the node relationship between velocity and viscosity, that solves for viscosity. So that was in water. Now we'll look in glycerin. So we see it's moving considerably slower, viscosity is considerably higher, so there's much more drag. What I like about this one, it's slow enough to connect to see what's going on. You actually see the flow around this object. And it's actually considerably different than what's going on. We'll go back to the water flow. It's considerably different than what's going on with the water flow. Again, we'll see if we can make some statements about what's going on here just from looking at variables and their dimensions. This is actually for a class project. So let's just go back to the water for contrast. So we're going to see it move a lot faster. We're also going to see, we look close at maybe you can't quite see, blurring this video with the character close like that. Well, we can understand something about that just from looking at it. That's for for a heat flowing through water with heat flowing through a fluid completely surrounded by that fluid. So this video is going to talk about there's something that we're not going to explain with dimensions and units, so this is the application of an interesting extension of active silicon. So I'll talk about this. So this is how we can actually reduce the drag or reduce the force felt by, for example, a sphere as it's falling through water by playing around with it.
You take a normal sphere and drop it in water, you'll see that it doesn't entrain any air behind it. And so you don't get a projectile that looks like a torpedo or anything. You just get a ball falling through water with a little tiny bit of air bubble. So what?
Right, and that's what we looked at in the previous video, and that's what we're going to talk about. That's the example we're going to talk about today is a ball falling through some kind of viscous fluid, and we're going to learn something about the ball falling through that viscous fluid. But now we're going to talk about no slip condition actually, and how we can manipulate no slip to reduce the force felt by that little ball.
What if we don't let the water contact the sphere? Now there's two ways to do this. The first method is by heating up the sphere extremely hot so that you get the Leidenfrost effect. The Leidenfrost effect is when you have a large temperature difference between your solid and your liquid that it's in, so that it flash boils it extremely fast and the liquid never actually contacts the solid surface. In order to do that, you need water that's close to the boiling point of water, and you need a really hot sphere. But a better way to do it is just to use a ball that's extremely hydrophobic. Then when you drop it in the water, the air will stay around the ball, it will entrain around the ball, and it should make a torpedo-like shape as it drops through the water. In order to make my sphere super hydrophobic, I'm going to be using a powder called lycopodium powder. I've used this a lot in the past on my channel. It's an awesome powder that's actually made of mold spores, but when you put it on water, whatever you dip through it, it makes that thing hydrophobic. So let's see what it looks like when I drop a still ball from this height above it. So it's going to be going pretty fast by the time it hits the water. So it's going to entrain a little bit of water with it. So let's see what that water looks like around the still ball. First, we'll try a normal ball. It's not hydrophobic. Okay, 3, 2, 1. So you can see there was almost no air bubbles when the ball fell in. Okay, now what I do is I just poured my lycopodium powder on the top here. 3, 2, 1. Bubbles.
Considerably faster, right?
Okay, this is so cool. You can actually see as it falls through the water, it makes this torpedo shape, this teardrop torpedo as it falls through the water. If your ball's not hydrophobic, you don't get that entrainment of air and that torpedo shape around it all.
So now he goes on in this video, I think, to say that this is, that when the ball is falling through water on its own, we have what's called the no slip condition. That has a demonstration for everybody who saw of the no slip condition. And that gives rise to a large fraction of the drag around the ball, and that's true. And so that's something we talked about in chapter 7, how basically the no slip condition and the viscous force that the ball feels is a key component of its drag. And then he says that we're violating the no slip condition because the fluid, the liquid water is not contacting the surface of the ball. But in what way are we not violating the slip? There's still, what else is going on? So we have, well, yeah, I heard a murmuring. What's that? It's two fluid. What's the second fluid? Air. Yep. And that air is in direct contact with the ball. And so the in this case, where the we have this kind of torpedo-like shape, the air is in direct contact with the ball. So we have the liquid in contact with the air. So we have an air liquid interface. And the air is in contact with the ball itself. And so there's no substitution between the air and the ball. And that's just providing much lower drag. The viscosity of the air is much lower than the viscosity. Yeah. So you're just drop a ball in the air next to a hydrophobic ball in the water, and you can make it stay away. I think so what means you drop the ball in air versus the ball in water with the hydrophobic thing. Which one would go faster than the same? This ball is still experiencing drag from the fluid. It's just experiencing drag from the fluid on shape. It's about a streamline. This shape, it's connected to bubble shape, it's almost streamline. And so this one we still go a little bit slower. We know this faster. Okay, so just as we hear where we're going, this video talks about dimensional analysis, and one of the most famous examples of dimensional analysis, which we'll walk through the setup of this video. We'll revisit this example problem once we learn how to do dimensional analysis ourselves. But I think this is probably the best exploration of what we can do, or what the power of dimensional analysis is.
In 1955, the United States conducted a test of an atomic bomb called the Turing test. Here's the footage, and you can see it is a really big explosion. But the question is, how much energy is in that explosion? Turns out that the United States did not release all of the data about the explosion. They only released 50. And as a result, if you're in the world, you want to know how big the explosion was, you're going to have to do some sort of mathematics modeling to estimate that. A British physicist called Sir G.I. Taylor did such a mathematics model using an extremely simple technique called dimensional analysis that I'm going to introduce you to the video. What he did was that he looked at a lot of screenshots from this video. He made a series of stills released as well, like this. If you look at one of these stills, you can see that there is a distance recorded. From that distance, you can figure out what the radius of this possibly hemisphere-sized explosion was. And there's also times radius. So you can know that at any given time, what is the radius? So what this physicist first did was he collected all of these different radiuses and times, and from that you can actually graph, and you can show what the relationship between radius and time is. So the problem here is we don't yet know what the energy is. And we look at these problems, we can say that this radius depends on perhaps many different variables. Clearly it depends on time, but it also depends on the energy of the explosion. A bigger explosion has a different relationship between the radius and time. And it also depends on perhaps many other physical properties. One that we studied was the density of air. If you have the air being more dense, it's going to sort of resist the explosion. So what you get out of this is that the radius is some function of time, of energy, and density. And the question for us, our goal is, what is that function? So what we're going to do is we're going to use dimensional analysis to try to describe what that function must look like, because at the very least, it has to have the right units.
So, so just to reiterate, this was, those, images, that, we looked at there, they were published in Life magazine. It's a very popular magazine, so widely distributed, but the energy of the explosion itself was one of the most highly guarded nuclear secrets of the time. What this British physicist, G.I. Taylor, was able to do, was just look at the dimensions of the variables that he knew must be involved in this. And from that, and those photographs that were publicly released, they actually make a very accurate estimate of the energy of that bomb. So we're going to revisit this once we've learned a little bit more about dimensional analysis. Okay. Yeah, we will be able to reproduce this kind of idea. Okay, so now we are in chapter 5, dimensional analysis. So in our chapter 1, we talked about dimensions, and the there we go. Just make sure my microphone is set up. Chapter 1, we talked about dimensions and the principle of dimensional homogeneity. We saw that come up on Wednesday as well, right? And so we can do more with that than just like nitpick manufacturer data sheets, right? So we can actually learn quite a bit more about problems, even when we don't know exactly what the physics are. We're also going to see that so early in this class, we started talking about Reynolds number. We kind of dropped off talking about it a little bit, but it's going to come back in a big way from here on. And we'll actually look at one way to think about where Reynolds number comes from by doing dimensional analysis. So we're going to see that with dimensional analysis, we can essentially derive the form of non-dimensional parameters like Reynolds number that govern the physics of a problem. We can think of dimensional analysis as a systematic way to look at a problem. Like we're going to look at the Navier-Stokes equations, and using dimensional analysis, we'll be able to say, under some conditions, this set of terms, like for example, the advective terms, may be small and therefore they can be ignored. And we'll be able to say under what conditions they are not small and can't be ignored, based on basically, again, this concept of dimensional analysis. It'll tell us conversely which terms in an expression or an equation are important and therefore have to be kept around. Another thing that we're going to look at is how we can take our, some kind of results, like experimental results, or some kind of observation that we have, like, for example, the like photographs of a nuclear bomb explosion, and how we can take those results and express them in a form with the least possible number of parameters, which is going to allow us to generalize the things that we observe. In the case of G.I. Taylor, it allowed him to take some small scale experiments that he was conducting in a laboratory, use a single measurement from those small scale experiments to estimate the energy of that Trinity test. And we're going to use the results from dimensional analysis going forward as we're looking at, for example, drag within a pipe or friction within a pipe. That will all be based on dimensional analysis. When we're looking at drag around a sphere or external objects, the forms that we use are all going to be based on dimensional analysis. Another use is how to scale experimental results from a model to a full-scale system. So a lot of times if you're designing something, even if you're using CFD, right, which is a much more modern way of doing it, oftentimes you'll need some kind of ground truth from a real-world experiment. But
but it may be cost prohibitive to build a full scale system in order to just run a test to make sure that your CFD is performing correctly, for example. So oftentimes it's much more economical to use a model, right? A smaller scale model of the system. But now you have to make sure that you are that you understand how to scale results from a smaller scale model up to what you would expect to see in the full scale system. And you can do that using dimensional analysis and non-dimensional parameters. And then finally, when you are using computational fluid dynamics, a form of the governing equations, for example, if you take the Navier-Stokes equations and we put them into a non-dimensional form, and we properly scale, and we'll talk about scaling variables, but when we properly scale our variables, we often end up with a form of the equations that's actually easier to solve numerically. As in, if you remember, or if you think to computational methods, there will be fewer, if you have properly scaled and non-dimensionalized equations, you'll often have fewer numeric errors. Basically, you won't be considering, if your equations are properly non-dimensionalized, then instead of having some numbers that are order 1 million and some numbers that are order 0.01, everything will be roughly order 1. Everything will be roughly around magnitude of 1. And that makes the numerics of the problem a lot easier to solve for a computer. So dimensional analysis is based on, again, just based on dimensions, right? Something we talked about in the first week of class. And the basic equation that we're going to look at today, as I promised, is far simpler than Navier-Stokes, but there's considerable power in this kind of simplicity. Okay. So let's return to this idea of dimensional homogeneity. So if we have a Bernoulli equation in this form, so P over rho plus 1/2 B squared plus GZ is equal to some constant. So we know that this expression is more or less comes from energy, right? So this is telling us a statement, this is basically a statement of energy balance within the fluid. Assuming no heat, no work, no friction, we're saying that the energy within the fluid is equal to some constant. But let's look at the dimensions of this system. Does anyone know what the dimensions of this equation, each term in this equation have to be? Anyone want to volunteer? What are the dimensions of each term in this equation? Length squared over time squared. How do you know it's length squared over time squared so quick? Because velocity squared, so two things, right? Velocity squared, we know velocity is length over time, right? And so velocity squared has to be length squared over time squared, right? So you know that one. But how do you know that that's the same as GZ? Because they're added, right? And every term has to be dimensionally homogeneous, right? So by inspection, this one's the easiest one to look at. We don't have to deal with kilograms or anything or mass. Yeah, so then we know if this equation is correct, then it must be dimensionally homogeneous. So those dimensions, just to review, are based on the variables that are present in the equation, right? Pressure, density, viscosity, and so on. In this case, each term has dimensions length squared per time squared, right? So one thing we hit on this, but I just want to reiterate now that we've had some more practice with dimensional homogeneity and dimensions. So if you're writing out the Bernoulli equation, you're trying to remember the Bernoulli equation, and you get to this last term, GZ, and you forget, is it Z? Is it GZ or Z over G, or what exactly? What does that term look like? You can actually check yourself, right, by doing a quick dimensional check of that last term, right? And since you know the dimensions of this term, when you work this one out, you should check that you actually get length squared over time squared. In this case, we have length over time squared times length, so we end up with length squared over time squared, and we know we didn't mess that one up, right? So we're going to be manipulating equations. It's one of the tools that we're going to use in the dimensional analysis toolbook or toolbox. And when we start manipulating equations, we're going to have to maintain dimensional homogeneity throughout the expression. So The dimensions of the expression may change, but they're all going to change the same way. So for example, I can take this expression, I can divide through by G, right? I get a different expression of Bernoulli, basically, or a different expression of energy balance for a fluid with no heat, no work, no friction. And if we do the check here, dimensional homogeneity is maintained, right? And in this case, the dimensions of each term should work out to just length, right? Because we have length sitting there. And just as a reminder, our fundamental dimensions that we're going to be considering are mass, length, time, and temperature. Now, we talked in chapter 4 about deriving differential equations that describe fluid motion. And we said most of the time, if we assume isothermal and constant properties, actually, if we just assume constant properties, incompressible rather, then we can solve we can solve momentum and mass balance independently of the energy balance for the fluid. And in that case, we're mostly going to be in this class considering just what's going on in the mass and momentum balance, meaning that the dimensions of the primary dimensions that we're going to be concerned with most of the time are just going to be mass, length, and time. This is going to be important in a few slides. And then if we are also considering energy balance, then we're also going to throw in this temperature dimension as well. Just want to come back for a second here. So the principle, what we're learning here about dimensional analysis, you're learning it in fluid mechanics, but it's applicable to all physics that you will encounter. So in heat transfer, right, you can do very similar kinds of analysis in heat transfer. It's one way of arriving at all of the non-dimensional numbers that you've been dealing with and that maybe you're trying to keep track of for the exam later today. In that case, it'll work in mass transfer, right? When you get to mass transfer, there are possibly other dimensions than these 4 as well, right? So for example, there could be a dimension for concentration, right? If you're looking at mass transfer. These are not the only 4 possible fundamental dimensions in all of physics. We could also have like charge, like things related to charge, or light intensity as well. But in fluid mechanics, these are the 4 that we're considering. And again, most of the time we just have mass, length, and time. So one of the primary goals of dimensional analysis that we'll see is to take expressions that we're dealing with and rewrite them in terms of dimensionless numbers. So we're going to take equations like the Navier-Stokes equations, and we're going to make everything in that equation dimensionless. So we're going to remove all the dimensions from that equation. And we're going to do that by basically, one of the things that we're going to do one of the tools we're going to use to do this is forming dimensionless numbers, which we're also going to call pi groups. And this is denoted typically by the capital letter pi. Okay. These pi groups, or these dimensionless groups, can then be used to simplify a problem. So we're going to talk about, for example, a ball falling through liquid. So this comes from Album of Fluid Motion. And here we can actually see much more clearly than we could in that blurry video the details of the flow around this sphere as it's falling through a viscous fluid. And so in this case, if we, for example, know that the terminal velocity v of the sphere, let's say that's the thing that we're interested in, we know that it depends on, or we guess that it depends on gravity, the diameter, right? Gravity, because the higher the gravitational acceleration, the faster the sphere should fall due to gravity. The sphere diameter, right? Because we would expect that a bigger sphere might experience a different, even if we don't know it's bigger, but at least a different force than a smaller one. The fluid density, right? So we would expect that the heavier the fluid is, the harder it is for the sphere to push it out of the way. And viscosity, because the more viscous the fluid, I guess intuitively you might think of this thing having a harder time moving through it, right? Imagine the sphere going through honey versus water. It should be harder to move through honey. So if we pose the problem this way, we say we don't know the details of the flow around this thing, right? But we just know that these variables are involved. Then we'll show how we can use dimensional analysis to derive two dimensionless groups that describe this problem. One of them is going to be our old friend, the Reynolds number, right? In this case, written as rho VD over mu. And the other is going to be this Froude number, V over square root of GD. And we'll show how we can actually develop these two numbers. And what this is going to tell us is that in this problem, if I have two situations, like one where I have a sphere falling in water, and another where I have a sphere falling through honey. If I match these two numbers, then it's basically the same problem. So I would only have to measure, I would have the same scaled terminal velocity in both cases. But we'll look at more consequences of this. So one of the key tools, and this is where we get into the math for today, is what's called the Buckingham-Pi theorem. So one of the big questions in dimensional analysis is how many dimensionless groupings do I need to describe a problem? This is what G.I. Taylor did. He said, if these are the only variables involved, there's only one dimensionless parameter that describes this this Trinity bomb explosion, and so he just needed to measure one thing experimentally. In the falling sphere problem, we end up with two. But how do we get that number, right? That's one of the fundamental questions. And the Buckingham-Pi theorem says that if we have n variables, and they're expressed in j physical quantities, so j dimensions, j fundamental dimensions, mass, length, time, temperature, or some subset of those, then we're going to expect k is equal to n minus j. That's our math for today. K is equal to n minus j dimensionless groupings. Yeah, I know, this one's tough. K is equal to n minus j dimensionless parameters. Generally speaking, we need exactly k dimensionless groups. So this is the number that we're looking for, is k dimensionless groups. So for example, the falling sphere problem, 5 variables. We know that velocity is a function of, again, gravity, diameter, density. This should be mu. Should be Greek letter mu. I've written it out. I've spelled it out. So this is 1, 2, 3, 4. This one is also a variable. Velocity is a variable here. So it's 5 variables in this problem. All right, so n is 5. How many physical quantities describe this problem? So how many dimensions do we have in this problem? So let's go through and count. So we have length shows up here, right? Mass shows up, yeah, definitely in density, also in this viscosity. And we have time. Do we have temperature? No, so 3, right? So our J is 3, N is 5, J is 3, right? So we just have mass, length, and time. So we expect 5 minus 3 is equal to 2 dimensionless groups. Okay, yeah.
Do we mean that every one of them can be K or like K or?
It's in general, it's K or more. Yeah, there's cases where you can't describe it with exactly K. There's cases where some of these things become degenerate, is what we would say, and it's a little bit changed. I try to choose examples where it is exactly K, and for most for what we're going to look at in this class, we're going to get K. Yeah. So right, so K is equal to n minus j. K again sorry, n was 5, j was 3, and so we end up with 2 dimensionless groups. Yes.
Don't density and viscosity depend on each other, so what do you need both on this?
Yeah, so good question. So the question is, don't density and viscosity depend on each other? So how do we know that we need both? So they don't strictly depend on each other. I mean, you can, there's certainly some dependence, but if you were to add like glycerin to water, you would increase viscosity and not, you can dramatically increase viscosity and not change density that much. So you can somewhat vary density and viscosity independently. But I think one of the things that you're getting at here is kind of the dark art of dimensional analysis, which I haven't introduced you to yet, but is coming, which is, how do I know, right? Like, let's say, you're encountering this problem of a sphere falling through a liquid for the first time, right? How do you know that it's gravity, diameter, density, and viscosity, and not some other combination of variables? And part of that comes from experience, right? So you all get experience with dimensional analysis in this class, and you all know that often we generally have density and viscosity independently. When we have a viscous flow problem, we're going to be considering those things independently. So that's one way, is experience. Another way is experiment. So if you really have no idea, you can run experiments and see what variables are actually important. So actually, to get back to that G.I. Taylor example, one of the reasons he was able to do this, I mean, aside from being like a very smart physicist, is that he was actively working on experiments where he was creating shock waves within fluids. He was just doing it in really small scale. And so when he saw these pictures published with shock waves in fluids, he said, oh, wait, I know how to deal with that. And that's how he came up with the list of variables and was able to do this non-dimensional analysis, or dimensional analysis rather. So yeah, and another way is a little bit of intuition, and that's kind of how I'm trying to guide you through this problem so far, is talking through why these things might be important, so that you can make some sense of it yourself. But yeah, that is kind of that gets towards the dark art of dimensional analysis. Often it's trial and error, actually. So that's another way of doing this, is try some different groupings and see what works right in the real world. Yeah. Yes. If k were equal to 0, I believe k cannot be 0. K is equal to n minus j. I believe, I have to check this, but I believe if k is 0, then you cannot have a dimensionally homogeneous equation. And therefore it can't be physically described, and you're missing something. But I have to look into that. Yeah. You should not see k is equal to 0. Yeah, that means something's wrong. I mean, if you were to be, trying to analyze one of these problems yourself at some future point, and thought, oh, maybe I can use dimensional analysis, and you get to k is equal to 0, that means something's wrong, and you miss something, right? So if k were 0, then you're missing, right? Your n is too low, and you're missing a variable. But I'll double check the consequences of that. Yeah. K has to be positive. That's correct. Yep. Yeah. So k should be positive greater than 0. Yeah. And again, I'll follow up on that as well. So another thing here that we're going to see. So a consequence of this is that if we were to be running experiments to try to understand the terminal velocity of a falling ball, this dimensional analysis tells us that there's really only 2 things that matter. There's really only 2 groupings that matter. And so we just have to make measurements of those or vary those 2 groupings together in order to simplify the problem. And we'll see consequences of that with real data as we move through this section. So Yeah, and just my note here, which we made earlier, is that in this case, J is 3. And this is very, very often the case in mechanics, where temperature is constant or ignored. Okay. I wouldn't take it for granted. It's not always the case, right? We can sometimes have just mass and time or something. You know, we can sometimes have just 2, or sometimes there will be temperature involved. So don't just automatically assume J is equal to 3. But it is very often the case. Yeah.
So for the physical changing.
J physical quantities really refers to the fundamental dimensions. So the primary dimensions of the problem. So by physical quantities, we mean like mass, length, time, and or temperature. Mass in this case, yeah. So mass is involved in a variable, right, in rho. So yes. If somehow there was no dependence on mass, if none of the variables depended on mass, then we would not have M. Yeah. So the way to check this is to just go through and say, okay, D, well that definitely has L, right? G, that's L per T squared. That's a T, so I have a T. And then wait, do I have a mass? Yeah, I know this is mass per length cubed, so I have an M. Do I have a temperature? No, none of these have temperature in their dimensions. Okay, so I just have MLT. Okay, that's the way to practically figure it out. Yes. No, so this is something I alluded to on the previous slide, but to reiterate, in this class, we're only considering equations with up to 4 dimensions for the equations that we've developed. I think you will have some examples on homework where there may be some other dimensions to consider, but it should be stated what those are. And in physics, there are other dimensions that you may consider. So in mass transfer, you'll have a dimension of concentration, right? So something about moles, right, would be, that's not captured in mass, length, time, or temperature. And so you'd have to consider that. There's another dimension you may have to consider if you have an electrostatics problem, for example, based on charge, right? So there are other dimensions. It's just for the equations that we've developed in this class, we have these 4 that we're worried about. Yeah.
Sorry, it's kind of like, I mean, density is dependent on temperature, though, even though like in the units, right? So
Yeah, so density is dependent on temperature, but it's not in the units. So in this case, all we care about is whether or not it is in the units. Okay. So if we said though that temperature dependence of density mattered, then we'd have a T here as a variable, right? And then we would end up with J is equal to 4, right? But we would also have some kind of temperature here as a variable to consider.
it would be 6 minus 4.
It would still, in this case, it would still be 2. That's not always necessarily the case, but yeah, in this case, it would still be 2. But yeah, so yeah, even though we know that density in general, and especially even for a liquid, viscosity is a pretty strong function of temperature, right? But when we're doing this kind of dimensional analysis, don't get hung up on that, okay? Look at the dimensions of the variables that we're considering, okay? Just the dimensions of the variables we're considering. Any other questions? Okay. Okay, so as an example, let's say we expect that the wall shear stress in a pipe, so this would be the force exerted on the wall of the pipe by the fluid dragging past it. That's what we mean by the shear stress, right? So the fluid is viscous, it's flowing, and as it's flowing through a pipe, it drags past that wall because of the no slip condition. The force that it exerts is the shear stress. And this is going to be really important, for example, when we're dealing with flow through pipes in the next chapter. We're going to talk a lot about wall shear stress. Let's say we know that this wall shear stress is a function of a bunch of variables. In this case, we're going to say it's in general going to be a function of how far we are from the inlet to a particular pipe, so X. A function of the diameter of the pipe, a function of the mean velocity within the pipe, density and viscosity, right? and this epsilon here, which is wall roughness. So again, it's like the texture basically of the surface of the pipe. And you may not know this immediately, but let's say you've done experiments or something in the lab and you've determined that it must be these things. Okay, that's one way to come up with this. So now the question is, how many pi groups? Okay, so how many pi groups do I have to describe this problem, given that I know this, right? This is all I know about it. I don't know exactly what the functional form is of the shear stress. All I know is that shear stress should depend on these things. So I want you to discuss with your neighbors for just a couple of minutes before the end of class, how many pi groups should I expect? How many dimensionless groups should I expect? Please discuss. Okay, we're running out of time, and I definitely don't want to go over time because I know you have other stuff going on today. So what do we get for n? How many variables are there in this problem? 7. Okay, how many dimensions or fundamental quantities are there? 3. So how many pi groups? 4, right? Yeah. So 7 variables, 3 dimensions, so 4 pi groups. Okay. All right, and we are going to end on this point, setting us up for next week. So we know how many pi groups. The next question is, how do we find them, right? We said that for the falling ball, we get Reynolds and Froude number, but how did we get there? And that's the subject for next week. All right, good luck. Thank you.